Hello everyone, welcome to Great Learning. Here we are to learn regarding graphs in Python. As we all know, a graph is a visual depiction of a collection of things in which some nodes are interlinked to each other. The points that connect internally are called vertices, and the paths that connect the vertices are called edges. In this course, you will learn basic concepts of graphs, its types, and operations. Also, traversal algorithms like breadth first search and depth first search with their implementation in Python programming language. Excited to learn? Then why wait? Let's quickly start the course.
If you haven't subscribed for our channel yet, I would request you to hit the subscribe button and turn on notification bell so that you don't miss any new updates or video releases from Great Learning. If you enjoy this video, show us some love and do like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure you comment on this video any queries or suggestions. I'll be more than happy to respond to all of them.
Hello everyone, welcome to this video where we'll be learning regarding graphs in Python. So graph plays a major role in learning data structure. Especially we'll come across graphs in data structure for computer science. Apart from those, we use graph in many other different places. So let's see how does graphs help in order to make our work convenient and our codes presentable. So let's quickly check on the agenda of this video, what all we'll be covering in this particular session. So first we'll be learning regarding introduction to graph. So people who don't know what is graph with definition and with good examples will first learn the first step, that is what is a graph and how do we represent a graph. After that, we'll be learning regarding types of graphs. So there are various and variety of graphs. We'll know few of them, what are the different types of graphs available for us. So next, it's common graph operations. So as every element, like for example queue or stack or linked list, anything, they have certain operations just like pop, push, delete, insert. So something like this. So in graph also we have certain common operation we can perform on them. So we'll learn regarding those. Then we'll be learning regarding the applications of graph. Applications not in the sense of computer science directed towards one single stream. It's about real time examples where the graphs are used in general. So next we'll be going through the traversals of graph. So in order to move between one particular source to one particular destination, what are the different traversal medium you use? I'm asking about the real time, right? So you have different modes to travel. Sometimes you travel through your vehicle, through public transport, through auto, through metro. So you have lots and lots of options in order to reach from source to destination. Likewise, in data structure as well, for the graphs we have to travel from one node to another node. We have different kinds of algorithms. In those I'll be teaching you regarding BFS and DFS. So breadth first search and depth first search. We'll be learning regarding these and also implementing those in Python on Google Colab. After all this, at last, we'll be summing up with the summary what are the different concepts we learned in this particular video. So then why wait? Let's quickly start the graphs in Python. Let's see the first topic, that is introduction to graph. So graph plays a major role generally in various domains. First, we'll remember, as soon as we remember the word graph, it is the course maths. So we have that history of plotting bar graph, pie graph, and we are using graph sheet during our schooling days, also in college days. So graphs are nothing but a simplified pictorial representation for huge data. It is very easy for everybody in order to see a picture and grasp rather than reading 2 or 3 pages of theory which contains the same data. So that is where graph came into existence. Coming up to the computer science domain and data structure subject, graph plays a very important role. Generally, it is a part of data structure. So in order to arrange data in a good, understandable, quick access format, we use graphs. Okay, so graph is also called as collection of vertices and edges. So with a simple example, I'll show you what are vertices and what are edges in a graph. So generally we represent graph as G is equal to V comma E. So V is known as vertices or vertex and edge is for E. Generally, we have another name for these things. Vertex is also called as node and edge is also called as path, right? So this is the basic definition and symbolization of the graph we use in data structures. So next, I'll be showing you a simple example. How do you represent a graph? So it comprises of vertices and edges. So we have to make a vertex. So I'm starting with a simple vertex A. This is a single vertex and you connect these to one more destination, right? So another vertex. So there are two vertices now and one edge. Edge is nothing but the path between one vertex to another vertex forms one single edge. So this is E1, edge 1. Again, if you want to develop this particular graph, you can create one more node or one more vertex. This is edge 2, right? So this is third vertex. So generally, if you want to represent now, what are the different vertex you have in this particular graph G? For example, name this graph as G. So G has three vertex, that is A, B and C. Three vertices are there. Next you have edges. So what are the different edges you have? E1 and E2. So this is how you represent the graph in simpler format. And these are the basic elements you have to know in a graph. Now we shall be learning what are the different types of graphs we have. In general, we have so many types of graph where I'll be teaching you what does these graph mean and how do we represent these, right? So starting from the first one, that is the finite graph. What is the meaning of finite? It is countable, right? The countable vertices and the countable edges are present in a graph, then it is a finite graph. So I'll represent that here. Okay. So you have three vertices and two edges. 1, 2 and 3 are the vertices and you have two edges which is reaching from 1 to 2 and 1 to 3. So edges is equal to, I'll name it as E1 and E2. This is E1, this is E2. So it is countable. Number of vertices and number of edges are countable. Hence, this is called as finite graph. Right. Coming up to the next one. It is infinite graph. So infinite means which is not countable. So how do you represent these kind of graph? Quickly, I'll write down. Say this is a vertex and edges has no connection. So you can't know which edge is connected where and how it will go further. I might do this as well. I might stop here again. Again, I can extend this or I can extend this here. So this is how the infinite graph will go. It does not have any naming, any edges count, and it is very difficult for anybody to track how does this infinite graph goes and where it reaches. So this is the second type that is called infinite graph. So coming up to the next one, we have trivial graph. Trivial means a graph which is having a single node. single vertex is called as trivial. It is not having any edges, it is not connected anywhere, it is not used anywhere to connect to another node. So this single vertex is called trivial graph. Coming up to a simple graph. So simple graph in the sense, generally the graph which you write, like for example, I'm writing a node, two different vertices. So node A and node B, which is connected with one single edge, right? And again, I'll connect this A with one more node that is forming a edge 2, and the node name is C. Again, I connect C with one more node called D, which is forming edge 3. B and D nodes are again connected, which is forming edge 4. And A and D is also connected, which is forming edge 5, right? So, simple graph is nothing but it should have only one edge between two different nodes. It should not repeat, it should not go back, it should not connect multiple times from one single node to different nodes. So, this is called simple graph. If you could see here, A to B is one edge, again A to C is one more edge, again C to D is one more edge. It is not looping internally, it is just connected one at a time. It is only once, right? So that is about simple graph. Coming up to the next one, multi-graph. Multi-graph is just an extension of simple graph. I'm using the same graph, and if you could connect C to B, and again, if you want to connect from A to B, it is having multiple connections, right? This is one connection, this is one more connection. So multi-graph is nothing but nodes which is having one or more edges is called as multi or multiple graph. Coming up to the next one, that is null graph. Null graph is nothing but a graph or the nodes which we use in that particular graph is not connected with the help of the edges. It is just like the nodes anywhere and everywhere. I can just give you a simple example here. So you have node A here, again node B here, C somewhere it is present here, and D somewhere here. So it is not connected with the help of the paths or the edges. This particular type of graph is called as null graph. Coming up to the next set of graph that we have here is complete graph. So complete graph, what it will show? It will show a connection between every vertex to every edge. Let me give you a simple example. A, B, C, D. It is completely connected, right? From one node to different node. And it is also called as a simple graph as well. You can connect it here, and also you can connect it here. So it is forming a complete graph having no cuts between, cuts in the sense A, B, C. It is not having any unclosed element inside the graph. It is completely closed between node to node. Every edge is connected. So this kind of graph is called complete graph. Coming up to the next one, that is pseudograph. So what is a pseudograph? Pseudograph is nothing but a graph which is having a self loop, right? So A, B looping towards itself. For example, this is called as pseudograph. A graph in where the vertex in the graph is having a self loop is called as pseudograph. Coming up to the connected graph. Connected graph is nothing but a simple graph as well as a complete graph. So connected in the sense that every vertex in the graph is connected to each other in one or the other way, right? It is forming a complete structure. Hence it is called connected graph. So the next comes disconnected graph. Disconnected in the sense it is not having any connections. Disconnected and null graphs are same. It is just A, B, it is connected, C is not connected, somewhere D and E are connected. It is not having the link for C or A and B. Something like this. This is called as disconnected graph. It is not having a proper connection. It is existing, but it is not completely in touch. All the vertices are not in touch, right? So coming up to the next one, we have directed graph. As you hear the word direction, what do you remember? Arrow. Something indicated towards left, right, up, down, something with a particular symbol like this. So directed graph is nothing but a graph which is having a direction from which vertex to which vertex we have to do a traversal. We have to move. So it is showing us a directed path. A to B, from B to C, again from C to D, again from D to E. So we are trying to give the graph with directions with the help of arrows is known as directed graph. Coming up to the last type of graph for the session, that is undirected graph. Undirected graphs are all the graphs which is listed almost here, that is leaving null and disconnected. All other graphs are the undirected graphs. That means we are using only lines to represent the relation, the edges between the nodes. Nothing related to the arrow or any directions. These kinds of graph is called as undirected graph. So it is not having a particular way in which it has to travel, where it has to go. We can try to find with the help of the algorithms how we have to traverse between the nodes which is present in the undirected graph. It is left to the learners or users perspective. So this is all about types of graphs. Now we'll be learning regarding common graph operations. So operations on data structures is not limited to only on graph. We can perform various operations on various data structures. For example, we can push elements inside the stack. We can pop elements outside the stack. We can insert element inside the queue. We can delete elements from the queue. And if you want to do any operations for the strings, right, you can join two different strings. You can find the element inside the string. You can just sort the elements inside an array. You have various kinds of operations which you can perform. Likewise, in graph as well, we have few common operations which we can do. The first one is add node or add vertex. It can be understood any which ways, it is same. So adding a node to a existing graph is first operation which we can perform. Say for example, we have graph as A, B and C. If you use add node, and you can just add one another node for that particular existing graph called D. This is a new node. How did you add it? By using the function add node, right? So that is the first operation you can perform, add node. The second one is delete node or remove node. So already existing graph, for example, you want to remove some node. Say for example, I'm removing C from here. So what will be the graph? Graph will be A, B, right? So in order to remove a node from a existing graph, we'll be using remove or delete node. Okay. So coming up to the next one, we have add edge. Edge in the sense which is forming a new path, a different path on an existing graph. Say for example, A you have, and you have B, and then you also have C, right? So you want to add one more edge. You can form a edge here, put up one more node, and you can complete the graph, right? You can add a edge which is comprising of two vertex or vertices, right? So this is one single edge. You can add a complete edge to an existing graph. Then remove edge. Remove edge is nothing but just deleting one complete edge from the graph, which is comprising of two vertex, right? Two different vertices will be present for one single path. So we are eliminating one edge, means we are eliminating two vertices from the graph. So coming up to the next one, contains. If a node is present in a graph or not, it is containing a node or not, we'll check by using contains operation, right? Say for example, we'll take this particular graph which is written here. So does a vertex exist in this particular graph G? Whether graph G contains vertex A. So this kind of conditions will be solved by using contains operation. Next you have as edge. Has edge in the sense it is checking whether graph G is having the edge AC, right? It is having the path, or you can name the edge, whether the edge even is present in the graph G. So we'll be confirming and we'll be checking for the vertex by using contains. By has edge will be used in order to check for the edges in the graph. These are the common operations which we can perform on graphs in data structures. Now we shall see different applications where we can use graph. With our knowledge or without our knowledge, we are using graphs in our day-to-day lives. So let's quickly see where do we use graphs. The first point is Google Maps. Google Maps is a heart of traveler or people who don't know who in a new city where to travel, how to go. Everybody are using Google Maps, including Ola and Uber, right? So Google Maps is contributing towards the people who don't know to travel from one place to another place, which is a new place for them. It is a friend for a traveler. So Google Maps, the features, everybody have used it and everybody know how Google Maps work, but still I'm trying to give you a gist of how Google Maps work. Google Map will give you a route from a source which you have chosen to the destination where you have to go, right? And the route depends upon four different options majorly. The first comes car, next comes bike, then public transport, and then walking, right? Walking is the least priority because it is taking huge amount of time. Say for example, source is Bangalore and destination is Goa, right? So walking takes hardly 5 to 6 days maximum in order to walk. So that is the least priority. So you can also consider the second point, optimization. It is optimizing how fast or how soon you can reach the destination. So the next comes the last but second place. Third place comes for public transport. Either it can be via train or bus, right? So if you have an option, if it is an international travel also, it can come up with flight, right? So you will have this transportation facilities accordingly where you are traveling. Generally it will first show up train or bus, right? So this is the third priority, optimizing. Coming up to the next, bike or the two-wheeler, right? It will show generally the common numbers duration for both car and bike. So say for example 11 hours here and 11 hours here. So it is between you how you want to commute. Either it is your car or your bike. So this public transport might take more time than this, might be 14 hours or 15 hours. So depends upon how you are traveling, which route you are traveling. So every route, every option has a different path for you to choose, right? But it will first show you shortest path first, right? That is one of the feature of a graph, right? That traveling or mapping is nothing but it is having graphs like picture. Maps are nothing but the graphs which is represented via which route, which place, how much is the traffic, shortest path, or how long you have to wait in order to cross this toll, or every detail will be present in Google Maps. So graphs is majorly used at the first rank in Google Maps and Google Map APIs. Path optimization is interrelated to Google Maps, which is shortest path, which is not having traffic, which is convenient. Any problem which is there in any work in progress, everything will be shown in path optimization. Not only regards with traveling, path optimization is also you can implement for searching as well. For example, path is nothing but it need not be a physical road or physical place where you can travel, right? Either it can be a road transport, air transport, ocean transport, or water transport, anything it can be. Likewise in computers, if you come, right? So if you think regarding in that perspective, path optimization is nothing but if you search something, right? If you search something in a database, if you want to search something, how fast you will get the searched element on the screen. So optimizing the path, right? Either whether it is going via address of it, or via it is taking a keyword of it, or it is searching by using different kinds of data structures, whether it is a search, binary search, or a linear search, or if you are sorting, if it is a sort, bubble sort, or if you are using any other kinds of sort in order to sort. So all these things depends upon path optimization. Again, the graphs are used. If you come specifically for graphs, you have different algorithms. Whether you are going via knapsack or traveling salesman, or you are going, there are different types of many other optimizations which you can make. Coming up to the social media mapping. So here what happens, you have a beautiful social media handles, WhatsApp, Instagram, Facebook, Snapchat, whatnot, right? You have lots of social media access nowadays. Every kid has an access for social media now. But how do you optimize uh, good mapping you do, or how do you use, but you just know as a user a front end, how it looks, how colorful it is, how, what is the new trend it is going on. So all these things you will just try to grab, but at the back end, again social media is using graphs. How it is connecting you to the world, it is connecting you to your friend, it is connecting via chat, it is connecting via video call, it is connecting via normal call. So all the calls and video calls which you make in social media is connected from one source to destination. Again, graphs come into picture. Apart from that, you have different options in Instagram and Facebook nowadays. That is a marketplace, that is a shop, a virtual or an online shop where you can see the products and buy them. You can pay them via third party, or you can also pay them via WhatsApp payment. And also you can see a Facebook marketplace, you can extend your business, you can create your page, you can make it professional page, official page, and you can connect, you can follow people, you can do whatnot, many kinds of options you have in social media. If you search something, some product, you could observe that you will get advertisements regarding to those products itself. So it is having the connect between what all you do, what all you like, whom do you follow, what do you choose, where do you go, when did you travel, when did you come back, so what is the season, everything is analyzed in social media with the help of graphs. I'm not telling graph is the major thing, it is a part. Graph is used in order to do this analysis and mapping in social media. Coming up to the last part, that is transportation maps. What is this transportation maps? Generally, people who live in Delhi, Bangalore will get to know you use metro, right? So metro has different colors. One is purple, especially in Bangalore, purple, and you have green line, right? We call it as purple lane or green lane metro. And if you could see in a metro station, you can find a graph again there, a map again there. That is where is purple train is starting, metro train is starting, where it is reaching, what are the different stations you get in the middle in order to take this particular route. Again, green, it is same. Source to destination. What are the different stops you have in middle in order to travel from one source to another destination? Accordingly, you will take choose between the lines, right? Which line you have to follow, which lane you have to go. So these are the applications of graph which is available nowadays for everybody, which we are using, but we are unaware that graphs is used in these applications or in these process, right? So that's about applications of graphs. Now we'll be learning regarding traversal algorithms. Why do we use traversal algorithms? The first reason is in order to have a methodical travel between the nodes in a graph. So there are many traversal algorithms. Now we'll be learning regarding one of it, that is breadth first search algorithm. In breadth first search algorithm, we have a different way of approach in order to travel to the node, right? So before that, we shall know where it is used specifically. Breadth first search algorithm is generally used in order to find the shortest path inside a graph. That means, obviously, in a real-time example, shortest path means it is used in maps in order to take user from source to destination in a very smooth, shortest possible way. So that is the real-time application of breadth first search. So after knowing this, we shall see how does we use this breadth first search algorithm and how it will work. So I'm considering a simple example in order to make it more precise enough. So I'm considering a graph here, right? So it is having 5 different nodes, if you could see, and all are connected to each other. So I'm making this a directed graph. Okay, we are implementing the same graph in Python, a language as well, further in implementation process. So before that, we shall see in a layman perspective how does this breadth first search will work. So I'll be starting traversal with 6, the first top node, that is 6, right? I'm writing it here. And how does this travel? Before going further, I'll let you know. It will travel level wise. Level wise in the sense, first we'll be taking one single node. In that node, we'll be finding the neighboring nodes. After finding the neighboring nodes, we'll visit each neighboring nodes once. We are not repeating the visiting of nodes again and again, right? Once that has been visited, we'll go to the next level. Say this is level 1, right? 6 is level 1, and this will form level 2. For level 1, 4 and 8 are the nodes to be visited. But for level 2, what are the different nodes attached to 4 and what are the different nodes attached to 8 should be visited. So that forms level 1 and level 2 traversal. So that is how breadth first search algorithm will work, right? So quickly following this process, after 6, it will visit obviously the neighboring nodes, that is 4 and 8. Okay, next we'll be considering 4. If we consider 4, we have 2 different nodes attached to it. So again, it is 3 and 5. After completing this level first part, we have to go to the second part. So for 8, 9 is connected. So 9 will be visited, right? So this is how breadth first search algorithm will work. So after knowing this process, right? So let's quickly check out the algorithm. How do you implement this in Python language? So before directly going to implementation, let's understand the algorithm, which is English like statements. So it is understandable by everyone, and then we'll go to the coding platform, right? Hope I'm clear for this particular explanation. So let me go to the algorithm part. So in algorithm, if you could see, the first step is, right? So put any of the graph's vertices at the end of the queue to begin. So we'll be using queue, we'll be using dictionaries, we'll be using the statements, if and for statements, in order to create this particular program, right? First, what we have to do is we have to put the graph's vertices, that means nodes, to the end of the queue to begin, right? And then we will take the first item in the queue and add it to the list of the items that have been visited, right? We'll be considering all the elements at first, and one after the other will be visiting accordingly, right? So then we'll make a list of the nodes which has been visited, and we'll always have a backline system because it should avoid the cycle of nodes. That means a node which is already visited again, that forms a cycle. It is not a single visit node, it forms a cycle when it is repeating the visiting of the node. After that, we'll be repeating steps 2 and 3 until the queue is empty, right? People who don't understand with the help of verbal explanation, let me quickly give you a simple example with a simple graph, how this BFS algorithm will work in a graph with the help of coding implementation, with the help of coding ideas, right? So let's check out with a simple example, how do we implement this particular BFS algorithm in coding platform. So before going to the coding, so right now I explained regarding the theoretical part algorithm. So let me quickly brief you with a simple example and then we'll go for coding. So this is a list which we have made for visited nodes. Okay. And this is a queue, for example, right? So all these lists here will be considered as visiting list and all these are queues, right? So first I'm planning to start with A, right? So when you visit A will come to this list. Then according to the rules, all the nodes connected will be stacked up in this particular queue. So that is B, C and D. So next I'm visiting B. Again visiting node will be A and B. What are the leftover things in queue? C and D. And one thing you have to check whether do we have any elements or any nodes connected to these particular nodes. Yes, for C we have E. So what do? We consider E as well in further. So now we are visiting for C, right? So A, B, C. So now you have to see what are the connected nodes you have. So C has E. So already existing was D in the queue and we'll be adding this E next. Because we are not disturbing the D already existing in the queue, we are just adding it, appending this E node at the last. So after you visit C, the next turn is D. So here we'll always have the visited nodes listed in order to avoid visiting again and again, forming a cycle, right? So C and D is what we are visiting. So next you have E in line. So do we have anything for D connected? No, we don't have anything connected to D, right? So that is why we are not adding anything here. So the only element left over here in this queue, again this is queue, this is visiting list, so is E. That particular E is written again here. A, B, C, D and E. Now we have Q as empty, right? Q is empty. So we don't have anything in order to add up to this particular visiting list, right? This is how we implement this process into the coding implementation, that is by using Python. So let's quickly hop in. Again, I'll be showing you different steps, what to build, what not to build in that particular code, right? So let me quickly go to the IDE. Here we are using Google Colab, right? So here we have different steps listed in the implementation process. So still if people are not clear, so let me make here a stepwise implementation is my idea. So that is why I put up stepwise theoretical sentences so people can understand. What do you do in the first part in order to code for BFS in Python? The first step is we'll create a graph. So the graph which I'm considering is the graph which I gave an example while teaching. So the same graph I'm just considering. So in here you have to consider, so this is the graph created. You can't give the graph as you write. The hierarchical tree method cannot be used. So what do? We use list and we try to form the graph here. For 6 is the node where the graph is starting. For 6 we have two different child nodes, that is 4 and 8. Okay. Again, for 4, we have 3 and 5. Hope you can imagine that, right? So again, we have for 8, we have 9. And for 3, we don't have anything further. For 5, it has been connected to 9 and 9 is not connected to anything. So this is a simple graph where we'll be implementing BFS, right? So let's see the second step. Creation of graph is complete. Then we have to do two lists, which is visited node and the nodes in the queue, right? We have to have two different lists. So let's quickly see. Yeah, we have list to manage visited nodes, that is visited nodes. It has been created and queue initialization is done. Second step. Okay, then let's go back and find out the third step. So we'll declare a function with the arguments visited nodes, the graph itself and the node. We have three different elements to be considered, the parameters, visited nodes, the graph and the node. And then we'll be adding the visited nodes to the visited nodes list, and we'll be keeping other neighboring nodes in the queue as I explained in the example, right? That function will create here. So this is the main BFS function you have to see. So we have three different parameters as I mentioned, that is visited nodes, graph and node, right? So the function name is BFS. So that's been created, and visited nodes will be appending in the sense will be adding to the end of the list, right? Say first I started with A, then I added B, then I added C. So that is how we try to add, right? So Q will also append. By the time Q should also be appending simultaneously. As we visit the node, we have to check any other further nodes is being derived from that particular node. If not, we'll continue. If it is there, we'll be adding the node to the end of the queue, not in the middle, as I mentioned, right? So that function is written here. After that, we are creating a while loop sequence. So let me quickly see the fourth step for you. So we'll be creating a while loop sequence, and we'll be visiting the nodes, and we'll be removing as and when we finish visiting. So that is what we will do, right? One visit at a time. That's all. We are not repeating the visit again and again in order to avoid the cycle, right? So next you have while. We'll be popping the elements from the queue to the visited nodes as I mentioned in an example, right? So first A went from the queue, and what are the neighboring nodes we had? We had B, C, and D. Again, B went, C and D were remaining. When C went, we had one more node to be added because C was connected to E, right? So E is added to the queue. Then D visited, then at the last E got visited. So that is how it worked in a simple example I showed you. So here also in the same manner, we'll be popping every element for every visit. So that is how for each node visit, we'll be popping the elements out of the queue. So we'll be checking for the neighboring nodes with the help of this particular function here, right? In the graph, is there any neighboring node present? Is it visited or not? If it is visited, then we'll be putting it to the visited node. If it is not visited, we'll be putting that to the queue. That is how it works, right? After that, at the last, what is the last step? Let's see. Finally, we'll use the for loop to check the unvisited nodes and before appending them to the visited nodes, right? Is there anything left inside the queue which is not visited, so that we can put that into the visited list node? So that will be checked with the help of the for loop here, right? So we'll be checking for the neighboring nodes and visited and unvisited as I explained you. Then at the last, we'll be having a to print. So this is a last line of code where we'll be calling function again and again until unless the graph is completely traversed in breadth first search manner. So this particular line will help, and it will print the elements, right? We are printing breadth first search algorithm graph. Once it is completely visited, it will print as it is. So let me quickly run this program for you. So let's see how the output will be. Here is the output, right? So 6 will be visited first, then 4, then 8, then 3, then 5, and then 9, right? So this is how this particular BFS algorithm will work. Hope this was clear. Now we'll be learning regarding depth first search algorithm, right? So in this particular algorithm, how the traversal will take place between the nodes of a graph. So let me have a quick example for you before I explain you how this will work. So I'm taking a simple graph which is having 6 different nodes, right? So I'm trying to write the nodes here with a proper branching which is necessary. So it is connected. All the nodes are connected together. So coming to DFS. DFS will work in an approach where it is from top to bottom. So once it is started at the top, that particular lane should complete until the end. After coming to end, how does it go back? It will be using the method called backtracking method, which is already mentioned here, right? So once the depth is reached, it will again go back and check for the immediate neighboring nodes, and then it will try to travel, right? So I'm making this graph as directed just for instance, right? So this is how it is. Let me quickly start with the first node. I'm considering 6 as the first node. So 6 is here, visited, done. The next thing is we have to check the nodes which is connected to 6. 3 and 8. We cannot go to 8. We have to be in one lane. We have started at the top. We have to start again, continue with the next neighboring nodes, that is 3 and 4. 4 is in one lane. All 6, 3 and 4 is in one lane. Top to bottom we have to consider. So 6, after that 3, after that 4, and then how to go back to the next element. That is done with the help of backtracking. Immediately from 4, it has reached the bottom. Nothing is there after 4. So immediately we try to backtrack. So backtrack to the immediate node, that is 3. 3 is already visited. We need not visit again. So which is connected to 3? 5. So we are taking 5 as a next node. So it has changed the lane. It has come to 5. After this, it will check whether it is connected to any other element here. No, it is not connected anywhere here. So 5 is connected to 9. So directly it is 9. Okay. So 9 has anything? No children, no particular nodes connected to 9. Nothing is present here. So 9 has no further elements. After 9, it is backtracking to the immediate node, that is 8. It cannot go back to 5 because 5 is already visited. So it is going back to 8. So 8 was not visited. So it is visited now. Now the complete DFS traversal is complete. How do you say complete? Again, it is connected to 6, for example, right? So 6 is already visited at the first itself. So single traversal for all the nodes is being done. All the nodes are visited one time at least. So DFS, therefore, DFS traversal is complete. So this is how DFS will work with a simple example. So now switching up to the algorithmic implementation of DFS. So what do you need in order to implement DFS in Python is the task, right? You need list, okay? You need stack, and you need few statements. Statements in the sense it might be if loop, while loop, or for loops. So these are the requirements you want to have before you start coding for this particular DFS algorithm implementation, right? So let's understand step by step in an algorithmic way. How does this approach work in coding platform? Step 1. In order to begin, we have to create the graph. Okay. So once the graph is created, we'll place any one vertex of the graph on the top of the stack. Okay. Stack is one of the data structure which we use, right? Which is there on the top will be popped out first, right? Last in, first out. Last in, first out. So whichever is on the top will be popped out first. That is the nature of the stack, right? So coming up to the next point. At the top of that particular stack, whatever the element is there, it is considered as it is visited element or visited node. So it is considered to be visited. Then step 3, we'll have a list which is having nearby nodes, right? Nearby nodes list should also be maintained in order to put up to the stack immediately, right? Once it is on the top, it is visited. After it is gone, we have to push another element inside the stack, right? So we have to keep the list ready. See, for example, after 6, what was it? 3. After 3, what was it? 4. We have to keep this line intact so that it is not missing any of the nodes to be visited. We have to repeat this step 2 and step 3 until unless the stack is empty. That is actually the final step of our algorithm. So between that we have one more step, that is step 4. So stack the ones that aren't in the visited list of vertices at the top. So as I told you, whichever it is not visited, we have to stack it as a top element for the stack, right? So then it is considered to be visited. After that, until unless the stack is empty, right? It is depleted. Until unless it is depleted, nothing but empty. So we have to keep on repeating this process, checking for the neighboring nodes in the list, putting that onto the stack, checking and putting back to the top of the stack. So this process will be working until unless the complete stack and complete neighboring nodes are complete. So this is the algorithmic picturization of DFS. So before hopping into the code again, all these explanations which I made theoretically, let me quickly give you a simple example with a graph and having stack and visiting nodes. How does this work? So here is the simple setup for you in order to understand how DFS will work inside a coding platform, right? So we are trying to understand in a layman's perspective how this traversing will happen. So I'm starting with a naming of these boxes. The first set of box, I'm trying to name it as visited list. Okay. So whatever the nodes visited, we'll list it out here. So the next set will be stack. Our stack, which is having the neighboring nodes which is to be visited. Unvisited nodes will be present in stack. Likewise, I'm doing it here as well. So hope this is clear. So this will consider as first iteration, second iteration, third iteration, fourth and fifth iteration sets. This setup is clear. So let's start with the node A in the graph. When you start node A as a visited, if you consider any node in this graph as visited, it's not that you have to put up only A as visited, you can take any of it. So to keep it clear and precise, I'm taking the first node, top node as a visited node. Once you consider that as a visited node, next thing you have to see whether it is connected to the child nodes, whether it is having neighboring nodes. Yes, it is having. What are the neighboring nodes we have? We have B, we have C, and we have D. Okay, so next immediately we have to go towards the depth of this particular node. The second node which will be visited is B. So what is left out? C and D. Okay, your responsibility is to check whether the node has further divided into subnodes or children. For B, check, nothing is there. For C, you have E. So now you cannot go to D. You have to consider, when you go to C, you have to consider the E, which is an immediate neighboring node for the node which is visited, right? So let's quickly see how it is. A is done, B is done. The next, which is on the top of the stack, is C. So C is a visited node now. Okay. So D will come to stack accordingly. Top of the stack it will come. But if you see here, C has one more node which is attached to it. That is E, right? So this particular E will take precision. It will be preceding the already existing element D. So now the stack formation will change, right? So now immediately it should visit E, not D. So this will become E and D will be pushed aside. So let me quickly give you a picture. A is visited, B is visited, C is visited, but now the top of the stack is E and then it is D. So what do? Next visiting should be E only. So what is left out here? D. So A, B, C, E and D. So all the nodes are visited. Hope this was clear, right? So how did it go to D? I just telling you. After E, it backtracked. Further, there is nothing. So it backtracked. C is already visited. Again, it backtracked. A is already visited. So the next neighboring node for A is D. So D took the second place, wherein E took the first place. So this exchange happened because of the priority, because of the rules, right? DFS work in that way only. Immediate neighboring node should be considered on the top of the stack. Whatever it is there in the top of the stack, it is considered to be a visited node. We'll be putting that to the visiting list. So this is how the DFS will work internally with a simple example. Hope this is very clear. Now we shall quickly switch to the coding environment where we'll be working on this particular DFS algorithm implementation with the help of Python programming on Google Colab. So this is how it will work, right? So here also I've mentioned few steps in order to make it clear enough in order to get a good picture of this particular algorithm. Step one, what you have to do while you code for DFS algorithm. Step one, we'll have to create the graph. Let's check out. The graph is being created. So as I told you, graph cannot be put up in a tree structure inside coding platform. We have to give the connects which we want to give from node to node. Say for example, 6 is connected to 4 and 8. This is understood. 6 is a parent node, 4 and 8 is a child node. For 4, again you have certain nodes attached. So for 4 you have 3 and 5. That gives you a clear picture in your mind how it is forming the graph. For 8 again, there is 9. There is one single child there for 8 also. But 3 further does not have anything. 5 is connected to 9, right? So 5 is always connected to the 9. 9 is very connected to 8. That is the cycle. So 9 further is not connected anywhere. So this particular picture which I wrote in an example has been used here. So that graph has been created. So the second step is we'll be having list or set in order to store the values of the visited nodes in order to maintain the track of the graphs which is visited. I mean the nodes which is visited in the graph. Okay. So that is step 2. As I mentioned, the first set of boxes of lines, that is visiting list or visiting set, which I mentioned in example, that is there. The next one, we'll define a function that takes 3 parameters. You have to consider 3 different parameters. One is visited nodes, one is graph, one is node, right? So after that, we'll use if condition and we'll try to create a function where we'll be having the list of nodes which is not visited in the graph and how it has to traverse. We'll be writing that particular function. So at step 5, we have to travel to the node which is there in the graph which is nearby to each other for the visited node as well. So once you visit something, right, anything connected to that particular node should also be considered. So this is how DFS will work. So let me quickly give you the picture. So I told you in order to track the visited nodes, we are using sets, right? We are using the sets here and then we are trying to find a function for DFS where we'll be considering visited or not visited. If it is not visited, then we have to just give that particular node into the stack so that it will come to the top of the stack and it is considered to be visited. And then again, at last, we have to print all the elements which has been visited. So this is about the DFS algorithm, how it will work in Python programming. So let me quickly run this program for you so that we'll be having a picture how this output will be there. So it will go depth wise. I told you it goes from top to bottom. So that is how it will work. It takes a few seconds to work. So let's quickly see. Right. So you have an output here. This is the depth first search visits it will make. So 6, after 6 it will go to 4, followed by 3, 5, 9 and then 8. Right. So that is how it will work, just like a format which I explained. So this is all about DFS algorithm. Hope this was helpful. Now we have come up to the last part of this particular tutorial. So let's have a quick summary on what all we learned in this video, right? So the first thing we started with what is a graph and with a simple example and how is graph notated, that is G is equal to V comma E, and we also saw different types of graphs and accordingly the meaning and the definition was told, naming a few, that is finite, infinite, simple, complete, connected, unconnected graphs and many more. So this was the first part. The next part we started learning regarding what are the different common operations we can perform on graphs. Likewise, queue and stack, push, pop, insert, delete operations. What can we do in graph? So we can do adding a node, we can remove a node, we can check whether the node is present in the graph or not with the help of contains. And we also saw does the edge exist. If we want to check that, we have to use has edge, and we can also add edge and remove edge. So all these basic operations were introduced in common graph operations. The next part was applications of graphs. In day to day life, where do we use these graphs? These were used in Google Maps, in social media, and many more places. Indirectly or directly, we are using graphs. So, this introduction was given in application of graph. After that, we came to the main part of this video, that is traversal methods. We have different types and methods in order to travel from node to node in a graph, right? So, those particular traversal methods were listed. So majorly we concentrated on BFS and DFS. So first we learned with a simple example, and then we went for algorithm and how do we implement this particular BFS and DFS into the coding platform. Before implementation part, we also saw how does the present working condition of the graph inside BFS and graph inside DFS. So with the help of queue and visited lists and all, we just try to explain before going to the implementation part. After this was done, we implemented BFS and DFS algorithm in Python with the help of Google Colab IDE, and we also got to know how does the node traversal will happen separately for BFS and separately for DFS. So all these things were taught in this particular video. So Sneha here signing off. Thank you.
If you haven't subscribed for our channel yet, I would request you to hit the subscribe button and turn on notification bell so that you don't miss any new updates or video releases from Great Learning. If you enjoy this video, show us some love and do like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure you comment on this video. Any queries or suggestions, I'll be more than happy to respond to all of them.